Now, we've spent time using both grammar-based approaches with hierarchical tree structure and sequence-based approaches using recurrent neural network mechanisms from deep learning to look at language structure at the level of the sentence and model it. And there are many ways that you can imagine bringing these two insights and toolkits together. And I want to spend a little bit of time describing one of them, which I think is a really interesting proposal and approach. In order to understand this kind of approach, the first thing you're going to want to do is recognize that a tree structure can actually be represented first projected down to a string, where we preserve the left to right linear order of words, but we also annotate the string with what we would call constituent boundaries. So in this case, this hierarchical tree structure has constituent boundaries noted before and after the beginning and end of each constituent. So for example, the string, the hungry cat, is a noun phrase, and there's no other phrase below that which dominates the entire substring. And so there is a direct annotation of open brackets NP, close brackets around the string, the hungry cat, saying that that is a noun phrase. Likewise for the other constituents all the way up to the top, where the entire string is dominated by the node S for sentence, and the outermost brackets with the annotation of S on the opening bracket is an annotation of that. And so you can project down a hierarchical tree structure down to a string representation like this. That's very convenient and affords a next step, which is to recognize that actually the tree itself can be seen as an action sequence. This is actually quite close to the notion of a sequence of derivation steps that we've seen earlier in the semester when we talked about traditional context-free grammar representations, but this is a different kind of sequence representation of the incremental generation of a tree. In particular, this is a very highly incrementalized top-down, left-to-right action sequence representation. In order to sort of tally the inventory of types of actions that are necessary for a context-free grammar, there are 4 classes that are necessary, and we can think about them as follows. So the first is going to be the generation of a non-terminal symbol. And for this representation of an action sequence mechanism, it'll be useful to think of a stack of incomplete constituents that persists during the structure of the tree's generation. The action non-terminal x, nt of x, says that I am going to push a new open non-terminal on top of the stack. Open means that not all of the internal contents of that non-terminal node, that is, the contents that are dominated ultimately by that non-terminal node, have been generated yet. That's what it means to be open. And the stack, it'll become clear on the next slide, but the stack is simply the set of nodes that have not actually been completely disposed of in the action sequence. This action can be seen as generating from left to right a new piece of the string representation of the tree. So that's open parentheses x. So we've created a new non-terminal node x, but since we haven't closed the parentheses, we're not done with it. Another possible action is gen of w, where w ranges over all of the possible words in the vocabulary. Here, the meaning of that is to generate a word w as a terminal node and put it on the top of the stack. And we're going to call it a closed node, which means that it can't have any internal contents itself. That's because a terminal node itself doesn't dominate anything. And that will be, the string gloss will be, I would simply append the word w to the string. The reduce action says I'm going to pop the closed nodes from the top of the stack in sequence that I encounter until I encounter an open node, and I will close that open node. And that's simply, that sounds complicated, but in the string gloss, it's actually very simple. It's just close brackets. And all the closed nodes themselves will not be impacted, but the open node, the first open node that you'll encounter going to the left from the top of the stack or the end of the string is going to be closed by this. And then finally, the last action is end. And you can only do end if the sole element of a stack is a closed S element. And there's no string gloss necessary. That's basically just the string is over. And so this is an action sequence inventory. And we can actually go from that to looking at what the generation process would be for an example tree. And hopefully this will illustrate the action sequence representation of an incremental left to right tree generation process. So we start off with an empty stack and no tree. And what's obligatory at this point, when there's nothing on the stack and there's no actions in the history, is you have to generate the root node in the grammar as an open node. So that'll be NT of S, generate an open non-terminal. And so in the stack representation, you can see here that I've put this open S node on top of the stack. I'm also over here going to give you a tree representation of what has been generated so far, and the nodes that are highlighted in blue will be meaning that those nodes are still open. And I'm doing that just to help you understand the correspondence between the stack representation and the incremental tree that it's understood to represent. So going forward from that, the next action might be, for example, NT of NP, so that is generate a new non-terminal NP. That goes onto the stack as a second open NP element. This little bar here says that these are two separate elements. So the vertical bar in this representation is the separator between stack elements. So now in the tree, we have two open nodes, an S and its first left daughter, which is also open. They're both open, and that is an open NP. The next action might be generate a word, maybe the word is the, and so I generate the here at this point. The, because it's a terminal node and it was a gen action, not a non-terminal action, this is a closed node. So it is not highlighted in blue, and there's no open bracket associated with it on the stack. You'll notice that the open bracket NP is separated from the in this representation by the vertical bar because there are two different elements on the stack. The is closed, NP and S before it are both open, and the is on the top of the stack at this point. We now might generate, for example, hungry. This will append yet another element onto the stack separated by a bar, and another element inside the open NP. Generate cat, same kind of action. And now here's an interesting next step. Pay attention to this. We now choose the reduce action. And the reduce action has a different effect. The reduce action says, I'm going to take all the top closed elements on the stack and take them and combine them with the first open element that I encounter, and then I'm going to close that off. So these stack element distinctions go away, and now I've got one stack element where I had four before, and it is closed. All right, and in the tree representation, notice that the highlighting on this blue circle, highlighting on this node went away because it is now closed. And that means that you can't add any more contents to the NP. Okay, and so once again, that's an incremental left to right generation. And conceptually, what we're doing is we're sort of traversing the tree incrementally, top down, left to right, and now we've sort of done everything that we need to do, that we can do. We've decided we're done with the NP, and we'll continue forward. Okay. So the next action might be, for example, generate a new open verb phrase, and then generate an open node chased, and so forth. We might generate a new open NP at this point, generate the word me. Now, if we reduce, we've now closed off the open NP. The next action might be reduce again, close off the open VP, close off the open S, and now we can use the end action. Once again, we can only use this when the sole element on the stack is a closed S node. That is true. This is the only element on the stack and it's closed. And we have to do this at this point. And so that's an obligatory action, and we take it and we're done. And we have a completed tree. This is no longer generable. Notice that there was an important distinction during this process between open and closed non-terminal nodes. An open non-terminal node was not done yet. You could continue to add daughters to it, append daughters to it. And once you closed it, you cannot do that anymore. That's an important distinction in the incremental tree generation process. Okay, so that's the action sequence, and this comprehensively determines the tree. Now, how do we make this a probabilistic model? Notice that if we were able to put a proper conditional probability distribution on action sequences, then we would have a probabilistic grammar. We would have a grammar that assigns a proper probability distribution to a space of possible trees. And we could do all of the ordinary things we've been doing earlier on in the semester with it as a probabilistic model over strings and over trees. It itself is very naturally incremental and so forth. And so the next segment of today is going to be a discussion of how we might do this, how we might put a probability distribution on this action sequence in a number of ways. And this will afford opportunities for integration with deep learning.